In 18th century, a lot of studies were carried out by various mathematicians to establish the lattice structure of various elements. Now, there are many elements which are very much useful for not only process industry but for all industries. So it was established that there are few type of lattices, for example, FCC, face center cubics, BCC, HCP. First, we need to understand what is lattice. It is nothing but a pattern of atoms which are there for any type of element. For example, if we talk about aluminium, nickel, copper, we will find that FCC is the basic pattern. For iron, manganese, chromium, we are having a BCC structure. For titanium, cobalt, zinc, we will be having HCP structure. So first we need to understand what these structures are, what they are doing, how they are impacting the mechanical and chemical properties of various metals. So we'll start with this thing and we'll try to establish how these atoms are interrelated and how these are packed, how much radius, how much voids are there, and how the voids are impacting the defects and metallurgy of various elements. So first let us see what is FCC. FCC is just a face center cubic where we have these atoms at the corners along with a atom at the center of face. So we call it face center cubic cell. In BCC we are having a additional atom at the center of the cube. We have atoms at the corners and atom at the center also. In simple cubic we don't have any atom at the face center and at the body center. So this is just simple cubic is just a pattern of atoms at the corners. So this is very simple, and along with this we are having HCP lattice also, where we have 6 atoms at the corner, 1 at the face, 3 at the body center, and same at the bottom also. So these 3 are the basic structures where whole metallurgy, especially for steel, if you talk about ferritic and austenite structures, that is BCC and FCC. So once we understand BCC and FCC structure, how atoms are packed, how voids are created, how the alloying elements are entering into those voids, we can understand many concepts related to mechanical properties, especially for example hardenability, toughness, weldability, tensile strength, yield strength. Everything is based on these structures. So let us see how these are interrelated with each other. First step will be to understand how the number of atoms are there in any of the unit cell. So how we calculate it, right? So if you talk about simple cubic, there are 4 atoms, 1 2 3 4. There is no face center, no body center. So this is very simple. So let us see how these atoms are contributing within one unit. Okay, so if you talk about these atoms will be only at corners. No, there is nothing at center, there is nothing at face. So each atom which is there at one corner is contributing 1/8 within the cell. So rest of the portion of the atom will be associated with other cubic cells on all directions, right? So that is why we call that each atom will be contributing 1/8 to a single cell. That means if any atom is there, 1/8 of that portion will be inside this cell, rest everything is outside. So we have 8 corners. So in simple cubic we can say we have 1/8 into 8. This is 0, this is 0, only one cell, only one atom per cell. So if you talk about any of these metals where we have FCC structure, this can be established that per unit there is one atom. Now let us see how the BCC structure is established. Now we have 8 elements, 8 atoms at all corners, which is contributing 1/8, and one complete atom which is at the center of this cubic cell. That means 1/8 and 1. So that means 2 atoms are there per unit cell. Same way, let us see how the FCC structure is maintained. 8 atoms at the corners, that is same, and it is contributing 1/8 towards that unit cell. There is nothing at body center, so we are writing 0. And if you see, we have 6 faces, and these atoms are contributing 50% towards this particular unit cell. So we are saying 1/2 into 6. So 3 atoms here, 1 atom here, so total will be 4. In HCP structure, again we are having same scenario. There are 1, 2, 3, 4, 5, 6. Again we have 6 atoms at the bottom, right? We have 2 atoms at the face and 3 at the body center. So we can establish 3 here, which are there inside the center. 1/2, which is half of face center, into 2. Then we are saying 1/6 of these atoms will be contributed into 2. We are having 2 faces, so we can conclude 6 atoms per unit cell. So this is the first step which we really need to understand. In BCC we are having 2 atoms per unit cell. In FCC we are having 4 atoms per unit cell. So this is something which is a basis which will be used throughout the metallurgy of BCC and austenitic structures, which is commonly used in process industry. So this is first step. We really need to understand how these atoms are contributing per unit cell. Now once we know how many atoms are there within that particular unit, now let us try to understand how these atoms are interrelated with respect to its radius and lattice dimension. If you see, for a single unit of simple cubic cell, these 4 atoms will be touching each other, and this is, let us assume, is a dimension of cubic unit A0. When these 2 atoms are touching, the radius of one atom and radius of another atom will be equal to the dimension of side of this unit cell. So we can say this A is equal to 2R. What we are doing, we are trying to establish the relationship between lattice dimension and the radius of the atom. Okay, so for simple cubic it is very simple. A is equal to 2R. And if you talk about, first let us see FCC, which is having atom at the center of the face. Now let us see, this dimension is A and these atoms are touching each other. So we will be having this scenario. So this is A, this is A. So Pythagoras theorem, we can easily establish this dimension, right? And the length of this dimension will be R, complete atom, that is 2R, then R. So this is A, and this dimension we know. So using Pythagoras theorem we can establish the relation between A and R. So A is equal to 4 by under root of 2 into radius of the atom. So this is established, very simple. Similarly, if you talk about the BCC structure, we can implement the same Pythagoras theorem twice. First we can utilize this dimension 90 degree and we can calculate the hypotenuse. Then we can use this hypotenuse and this hypotenuse and we can calculate the center. So we can establish this hypotenuse with respect to the dimension of the lattice, and we can conclude under root of 3 into A, that is the dimension of lattice, is equal to 4 into R, that is the radius of atom. So this way we have just calculated the relation between lattice dimension and the radius of the atom. right? So these are the basic steps which we really need to understand. First we need to understand how many atoms are there per unit cell, then how the radius of the atom is related to the structural lattice. Okay, so I'm sure this is clear, so that we can start looking at how these are packed inside the atoms.